For decades, scientists believed they had a clear understanding of how large predatory dinosaurs lived and hunted. However, the discovery of new Spinosaurus fossils challenged many of these ideas. Evidence revealed that this giant hunter was not only adapted for life on land, but was also closely connected to rivers, lakes, and waterways. This remarkable finding forced researchers to rethink long-held beliefs about dinosaur behavior and evolution. Spinosaurus, unlike most giant predators of the prehistoric world, possessed a unique combination of features that set it apart from every other known meat-eating dinosaur. With a long crocodile-like snout, powerful jaws, and a huge sail rising from its back, Spinosaurus looked more like a creature from another world than a typical dinosaur. Spinosaurus is a genus of very large dinosaurs that lived in the region that is now called North Africa, during a time in the late Cretaceous period known as the Cenomanian stage. This time happened about 100 million years ago to about 94 million years ago. During that long span of time, large land areas and river systems existed across what is now the Sahara region and nearby lands. These environments supported many forms of life, including large reptiles, fish, and other animals that lived both in water and on land. Spinosaurus existed in these environments and left fossil remains that became known to science through discoveries made in the early 20th century and later periods. The first known remains of Spinosaurus were found in the year 1912 in Egypt. These remains were collected from rock layers that contained many fossils of ancient life. After the discovery, the fossils were studied and later described in the year 1915 by a German scientist named Ernst Stromer, who worked in paleontology, the study of ancient life through fossils. The description provided early scientific information about the structure and features of this dinosaur based on the remains that were available at that time. These early fossils included parts of bones that helped establish the existence of a very large predatory dinosaur with unusual physical characteristics. The original fossil material that was studied in the early 20th century was later destroyed during the events of the Second World War, when many museum collections and stored scientific materials were lost. This loss created a major gap in direct physical evidence for many years, leaving only drawings, notes, and written descriptions from the original research. After many decades, additional fossil material of Spinosaurus was discovered again in the early years of the 21st century. These new discoveries came from different locations in North Africa and provided new physical evidence that helped scientists continue studying the genus. The new fossils included parts of skulls, teeth, bones from the limbs, vertebrae from the spine, and tail elements. These findings allowed researchers to understand more about the body structure and lifestyle of Spinosaurus than was possible earlier. Even with these discoveries, there remains some uncertainty about how many species of Spinosaurus existed. Fossil remains that have been reported in scientific studies may belong to one species or more than one species, and this question continues to be examined. The type species, which is the main reference species for the genus, is known as S. egyptiacus. This species is mostly known from fossil material found in rock formations in Egypt called the Bahariya Formation, and also from similar aged rock layers in Morocco known as the Kem beds. These geological formations contain many fossils from the same general time period in the late Cretaceous. Another named species, S. mirabilis, has been identified from fossils found in the Farak Formation in Niger. Some fossil material has also been suggested to represent another possible species named S. maroccanus, which was also found in the Chem beds. However, this name is widely considered doubtful by many researchers, and the fossils linked to it are often thought to belong to S. aegyptiacus instead. There are also other fossil names that have been suggested in scientific literature as possibly being the same as Spinosaurus, including Sigilmassasaurus from the Chem beds and Oxalia from rock layers in Brazil known as the Alcantara Formation. Some researchers think these names refer to separate types of animals, while others think they may represent the same genus. This uncertainty is still discussed in scientific research based on fossil comparisons and analysis of bone structures. Spinosaurus had a body structure that shows many unique features. The skull was long, low in height, and narrow in shape. The teeth were straight and shaped in a simple cone form, and they had little or no cutting edges along the sides. These teeth structure suggests a feeding style focused on gripping and holding prey rather than slicing. The front limbs were strong and well developed, with bones that supported hands containing 3 fingers. One of these fingers had a large claw that was more developed than the others. The vertebral column had tall extensions called neural spines that grew upward from the backbone. These spines reached very large lengths, with some measuring about 1.65 meters in length. Skin is believed to have been present between these spines, forming a continuous surface along the back region. The pelvic bones were reduced in size compared to the rest of the body, and the hind limbs were relatively short in proportion to the overall body length. The tail was long and narrow with tall, thin bone extensions and elongated structures underneath the tailbones that increased the height of the tail structure. The body size of Spinosaurus indicates a very large land-dwelling predatory animal. Scientific research published in the year 2022 estimated that S. aegyptiacus may have reached a length of about 14 meters and a body mass of about 7.4 metric tons, which is also expressed as about 8.2 short tons. These estimates are based on fossil measurements and calculations made from known skeletal parts. The size of the skull and teeth structure shows adaptation for capturing and holding prey items. The forelimbs and claws indicate strong grasping ability. The tail structure shows a form that could move through water with controlled movement. The bone density in the leg bones was relatively high, which would have affected how the body behaved in water environments, especially in relation to floating and sinking control. Spinosaurus is known to have consumed both aquatic and land-based animals. Fossil evidence, including tooth marks and stomach content indicators found in related discoveries, suggests feeding behavior that included fish and other water-dwelling organisms, as well as animals from land environments. The living environment of Spinosaurus included river systems, tidal flat areas, and regions with dense plant growth such as mangrove-like forests. These environments provided access to both water and land resources. Many other types of animals lived in the same regions, including large fish species, crocodile-like reptiles known as crocodilomorphs, lizard-like squamates, turtles, flying reptiles known as pterosaurs, and marine reptiles known as plesiosaurs. The presence of this wide range of animals indicates a rich and diverse ecosystem with many ecological interactions. The ability of Spinosaurus to spend time in water environments has been supported by several lines of evidence from fossil studies. Bone structure analysis shows that the leg bones had higher density than many other large predatory dinosaurs, which would have influenced how the body moved and behaved in water. The tail structure, with its tall and extended bone features, suggests movement in water environments through side-to-side motion. The long snout and conical teeth structure suggest feeding activity that involved capturing prey in water. The dorsal spines along the back created a large raised structure that extended along much of the body length. This structure may have had a role in body display or other biological functions. The exact function remains studied through fossil evidence and bone reconstruction work. The discovery history of Spinosaurus continued to develop after the early 20th century. After the original fossils were lost during the Second World War, there was a long period during which knowledge of the animal depended on early drawings and written scientific descriptions. Later discoveries in North Africa and other regions provided new physical remains that allowed renewed study. These later fossils came from different geological layers that preserved bones under conditions that allowed partial reconstruction of the skeleton. The combination of early descriptions and later fossil discoveries has allowed researchers to gradually build a more complete understanding of Spinosaurus anatomy and distribution. The fossil record shows that Spinosaurus existed in regions that had active river systems and coastal environments during the Cenomanian stage of the late Cretaceous period. Sediment layers from this time contain evidence of water flow, plant growth, and animal activity. Spinosaurus remains have been found alongside fossils of fish species that lived in freshwater and brackish conditions. The environment also supported reptiles that lived in both water and land areas. The presence of these fossils together indicates that Spinosaurus lived in areas with frequent access to water sources and varied ecological zones. The skull structure of Spinosaurus shows a long and narrow form that extends forward with a large number of teeth arranged along the jaws. The teeth are simple in shape and do not have complex cutting edges. The jaw structure allows for a strong gripping motion. The nasal region of the skull is positioned in a way that supports airflow during breathing while the head is partially submerged in water. The eye sockets are placed in a way that allows vision during movement through different environments. The neck region connects the skull to the body with vertebrae that support head movement and stability during feeding activities. The forelimbs of Spinosaurus are well developed with strong bone structure. The upper arm bone connects to the lower arm bones, which connect to the hand structure. The hand contains 3 fingers, and one of the fingers has a large claw that is more developed than the others. This claw is formed from a curved bone structure that supports grasping actions. The muscles attached to the forelimbs were likely strong, allowing movement and handling of objects or prey. The arrangement of bones shows support for activities that required reaching and holding. The spine of Spinosaurus contains tall neural spines that extend upward from each vertebra along much of the back. These spines vary in height along the body, reaching maximum length in the middle back region. The structure formed by these spines created a continuous, raised feature along the body. Skin tissue likely covered these spines, forming a connected surface. The internal bone structure of the spines shows growth patterns that indicate gradual development during the life of the animal. The function of this structure is still studied through fossil analysis and comparison of bone forms. The pelvic region of Spinosaurus is reduced in size compared to the overall body. The bones in this region are shorter and less massive than those of many other large predatory dinosaurs. The hind limbs are also relatively short, with bones that include the femur, tibia, and fibula. These bones support movement on land and in water environments. The foot structure contains digits that support weight distribution. The muscle attachment areas indicate movement capability that allowed walking and other forms of locomotion. The tail of Spinosaurus is long and extends behind the body, with tall neural spines and elongated bone structures along the lower side of the vertebrae. These features increase the surface area of the tail. The structure supports movement through water environments by allowing controlled motion. The bones show flexibility that supports lateral movement. The tail contributes to balance and movement control when the animal is in aquatic environments. The bone density in the limbs of Spinosaurus is higher than that of many other large predatory dinosaurs. This increased density affects how the body interacts with water. Heavier bones influence buoyancy and movement control in aquatic settings. The internal structure of the bones shows reduced hollow spaces compared to other related animals. This feature is studied through fossil cross-sections and microscopic examination of bone tissue. The environment in which Spinosaurus lived contained seasonal changes in water levels, plant growth, and animal activity. River channels changed course over time, and floodplain areas developed different habitats. These changes created a dynamic environment where animals adapted to shifting conditions. Spinosaurus fossils found in these regions provide evidence of long-term occupation of these habitats during the Cenomanian stage of the late Cretaceous period. The first possible finding connected with what is now known as Spinosaurus may have taken place in the month of October in the year 1898. During that time, a French geologist named Fernand Fourreau removed two unusual teeth from rock layers that belong to a time interval known in geology as the Cenomanian. These rock layers were part of sediment deposits located in the Jura escarpment region in the area that is today in southern Algeria, which at that time was under French colonial administration known as French Algeria. The rock layers in this region were formed through long natural accumulation of sediments over geological time, preserving remains of organisms that lived in ancient environments. These teeth were collected during the wider scientific and geographic journey called the Fourreau-Lamy expedition, which took place between the years 1898 and 1900. This expedition moved across large parts of the Sahara region, starting from areas in Algeria and continuing through desert regions toward Lake Chad. The journey included geological observations, mapping activities, and collection of fossil material. The teeth collected by Fernand Fourreau were among several fossil objects recovered during this expedition. In the year 1905, a French geologist named Émile Hoch examined fossil material that had been gathered during the expedition. Among the collected items were the two teeth that had been found earlier by Fernand Fourreau. Émile Hoch studied these teeth and placed them within a classification that assigned them to a fish genus known as Saurocephalus. This classification reflected the interpretation of the fossil structure at that time based on available knowledge and comparison with known fossil forms. Later developments in paleontological research led to changes in the interpretation of these teeth. In the year 1915, the German paleontologist Ernst Stromer re-examined the fossil evidence that had been associated with these teeth. Ernst Stromer reassigned the teeth to the dinosaur group now known as Spinosaurus. This reassignment placed the teeth within a different biological classification based on updated fossil interpretation and anatomical understanding. Over time, scientific agreement developed that supported the reassignment made by Ernst Stromer, although the original physical teeth were later lost and no longer available for further direct examination. The absence of the original teeth left later researchers dependent on written descriptions and historical records for information about them. The first fossil remains that were confidently assigned to Spinosaurus were discovered later, in the autumn season of the year 1912. These remains were collected by an Austro-Hungarian fossil collector named Richard Markgraf. He worked under financial support provided by Ernst Stromer and the Bavarian Academy of Sciences. The fossils were found in rock deposits belonging to the Baharia Formation located in the Bahariya Oasis in the western region of Egypt. The Bahariya Formation consists of sedimentary rock layers that were formed during the Cenomanian stage of the late Cretaceous period. These rock layers are part of a group of geological formations distributed across North Africa that preserve fossils from that time period. The environment represented by these sediments reflects ancient conditions that existed during the late Cretaceous geological period, which is part of the larger Mesozoic era. In the year 1915, Ernst Stromer formally described the fossil remains collected from the Bahariya Formation. He identified them as belonging to a new genus and species of dinosaur, which he named Spinosaurus aegyptiacus. The naming of this genus and species followed scientific naming conventions that use Latin and Greek language roots. The genus name Spinosaurus is formed from the Latin word spina, meaning spine, and the Greek word sauros, meaning lizard. The species name Aegyptiacus refers to the geographic region of Egypt where the fossils were discovered. The specimen that served as the basis for this classification is known as the type specimen, identified as BSP 1912 Roman numeral 819. This specimen includes fragments from several parts of the skeleton. These include portions of the lower jaw known as the mandible, a fragment of the upper jaw known as the maxilla, vertebrae from the neck region known as cervical vertebrae, vertebrae from the tail region known as caudal vertebrae, and vertebrae from the back region known as dorsal vertebrae. The specimen also includes structures such as neural spines, ribs, teeth and elements known as gastralia, which are bones located in the abdominal region. In the month of April in the year 1914, another expedition led by Richard Markgraf returned to the Bahariya Oasis. During this expedition, an additional fossil skeleton was discovered. This skeleton is identified as BSP 1922, Roman numeral X 45. The remains belong to a spinosaurid dinosaur, although the preservation state of the fossil was incomplete and the specimen was not fully intact. After the discovery, the fossil underwent a series of handling processes during the time of the First World War. During this period, the region was affected by administrative control under Anglo-Egyptian authority, and the fossil material experienced improper unpacking and repacking procedures. These handling issues caused damage to the specimen, reducing its completeness and affecting its structural integrity. Due to political conditions during the war period and strained relations between German and British authorities, the fossil material required a long period before it could be transported and studied further. The skeleton eventually arrived in Germany in the year 1922. After its arrival, Ernst Stromer conducted a formal description of the specimen in the year 1934. Ernst Stromer assigned this fossil to the genus Spinosaurus, but he identified differences between this specimen and the earlier described Spinosaurus aegyptiacus. Because of these observed differences in skeletal structure, he considered it to represent a separate species within the same genus, which he referred to as Spinosaurus B in his classification. In the year 1936, Ernst Stromer worked together with a researcher named Dr. Ehrhardt to create a reconstructed skeletal representation of Spinosaurus. This reconstruction was based on available fossil material, including the original type specimen, the specimen identified as Spinosaurus B, and related fossil taxa that were considered relevant for anatomical reconstruction. The reconstruction involved assembling known fossil elements and adding missing skeletal parts based on scientific interpretation of available material. The reconstructed skeleton was stored in the Paläontologisches Museum München, which is part of the Bavarian State Collection of Paleontology under the Bavarian Academy of Sciences. During the night of April the 24 to April the 25, in the year 1944, the museum building was severely damaged during bombing events that occurred in Munich during the Second World War. As a result of the destruction, many fossil materials housed in the building were lost, including the Spinosaurus specimens. Prior to the destruction of the fossils, there had been personal and professional disagreements between Ernst Stromer and the museum curator, which influenced decisions regarding the relocation of the fossil collections. Because of these circumstances, the fossils were not moved to safer storage locations before the bombing event occurred, which resulted in their loss. The scientific work of Ernst Stromer received limited attention during later years following these events. In the year 1995, the son of Ernst Stromer donated archival materials belonging to his father to the Paläontologische Staatssammlung München. These archives included photographs and documentation related to the original Spinosaurus fossils. In the year 2006, a research study led by American researcher Joshua Smith examined these archived materials. Among the archived items were photographs showing the type specimen of Spinosaurus. These photographs allowed researchers to study visual records of fossil material that had been destroyed earlier. Based on these photographic records, Joshua Smith concluded that earlier drawings made by Ernst Stromer in the year 1915 contained some differences in detail when compared with the photographic evidence. During the decades following the mid-20th century, additional spinosaurid fossils were reported from several regions across North Africa. These regions include Algeria, Morocco, and Tunisia. Many of these fossils consisted of isolated teeth, bone fragments, and partial skeletal remains. These discoveries provided additional material that contributed to the broader understanding of Spinosaurid distribution in North Africa. In the year 1986, scientific research published information about teeth discovered in Cretaceous rock layers in Tunisia. These teeth were assigned to Spinosaurus and represented evidence of the presence of this dinosaur genus in that region. In the year 1989, a French paleontologist named Eric Buffetaut examined fossil material from the Kem beds located near Taouz in Morocco. This material included jaw fragments and a tooth that were assigned to Spinosaurus species. During the 1990s, additional fossil discoveries of Spinosaurid dinosaurs were reported from multiple continents, including South America, Asia, Africa, and Europe. These discoveries included a variety of fossil elements such as teeth, vertebrae, and partial bones. These findings contributed to expanding knowledge about the broader group of Spinosaurid dinosaurs to which Spinosaurus belongs. Despite these discoveries, many aspects of the anatomy of Spinosaurus remained uncertain due to incomplete fossil preservation and fragmentary remains. Some fossil materials that had previously been assigned to Spinosaurus or to related genera, such as Sigilmassasaurus, were later re-examined by researchers, and different interpretations were proposed regarding their classification. These interpretations involved reassignment of certain fossils to other dinosaur groups based on anatomical analysis. Additional fossil material assigned to Spinosaurus was recovered from the Kem beds in the Tafilalt region of Morocco, near the area of the ancient settlement of Sigilmassa. In the year 1996, the Canadian paleontologist Dale Russell described several fossil elements from this region. These included cervical vertebrae, fragments of the mandible, and a neural spine from a dorsal vertebra. He assigned these remains to a new species named Spinosaurus maroccanus. The species name Maroccanus refers to the Kingdom of Morocco, the country where these fossils were discovered. The fossils were found in red sandstone deposits that are part of geological formations known under several names including continental red beds and lower chem beds. Among the collected specimens, a cervical vertebra catalogued under number NMC 50791 was selected as the type specimen for Spinosaurus maroccanus. The classification of Spinosaurus maroccanus was based on differences in the proportions of cervical vertebrae when compared with earlier known Spinosaurus material. These differences were measured through examination of vertebral structure and proportions. Later research on these fossils included further analysis of vertebral variation and consideration of fossil preservation conditions. Subsequent studies evaluated the status of Spinosaurus maroccanus and considered different interpretations of its classification. Some researchers continue to list it as a valid species, while others considered it a doubtful name or a synonym of Spinosaurus aegyptiacus or related taxa, such as Sigilmassasaurus brevicollis. Certain specimens originally assigned to Spinosaurus maroccanus were later reclassified as spinosaurid fossils that could not be assigned to a specific genus with certainty. In the year 1996, another study conducted by American paleontologist Paul Serino and colleagues examined fossil vertebrae previously associated with Spinosaurus B and Sigilmassasaurus. These researchers assigned some of these vertebrae to the dinosaur genus Carcharodontosaurus, based on interpretation of fossil association and anatomical structure. Their analysis included assumptions regarding the relationship between nearby fossil finds and skeletal reconstruction. Later research re-examined these interpretations and provided alternative classifications for the same fossil materials. Some studies continued to assign certain fossils to Sigilmassasaurus, while others maintained separate classifications based on revised anatomical analysis. In the year 2003, researcher Oliver Rauhut proposed that the original Spinosaurus holotype may represent a mixture of remains from different dinosaur types, including elements similar to Carcharodontosaurid dinosaurs and jaw elements similar to Baryonychine spinosaurids. Further discussion of these fossil interpretations continued across later scientific studies, with ongoing examination of fossil material from North Africa and related geological formations, and continued analysis of skeletal fragments, vertebrae structures, and jaw morphology, along with continued documentation of fossil distribution across sediment layers and excavation sites in multiple regions of the Sahara and adjacent areas. In the year 2008, a fossil collector from Morocco who was working in the region of Erfoud brought several broken and incomplete dinosaur bone pieces to the attention of an Italian scientist named Nizar Ibrahim. These fossils were not complete skeleton parts, but instead small and scattered fragments that still carried scientific interest because of their structure and form. The collector was based in Erfoud, a place in southeastern Morocco that is known for the movement of fossil materials through local trade and collection activities. When Ibrahim first saw these remains, he carefully studied their shapes and internal structure. He did not immediately assign them to a confirmed species, but he observed that their features suggested a possible link to a dinosaur group known as Spinosaurus. At that time, the identification remained uncertain, but the idea formed that the fragments might belong to that genus based on their general bone structure and the way they were preserved. In the following year, which was 2009, additional fossil material appeared that was more complete than the fragments seen earlier. These new remains were not just small pieces, but included several bones that together formed part of a partial skeleton. This collection of fossils was obtained by the Museo di Storia Naturale di Milano, which is often referred to by the abbreviation MSNM. The fossils were acquired through an Italian fossil dealer who had purchased them from the same source connected to the collector, who had shown the earlier fragments to Ibrahim. This connection created a link between the material, seen in 2008, and the new skeletal remains acquired in 2009. The fossils were stored and prepared for scientific examination within the museum's research environment. After the museum received the fossils, Nizar Ibrahim later visited the institution to examine the material directly. During this visit, he was shown the bones by Italian paleontologists Cristiano dal Sasso and Simone Maganuco, who were working on studying the fossils at the museum. Ibrahim carefully compared what he saw in the museum collection with the earlier fragmentary remains he had examined in 2008. He observed that the sandstone matrix surrounding the bones in both cases showed similar characteristics in texture and composition. This similarity suggested that the fossils may have come from the same geological environment. He also examined the neural spine structures present in the museum fossils and noticed that they showed similarities to earlier drawings and reconstructions created by Ernst Stromer in 1915. These observations led him to consider the possibility that both sets of fossils, the fragments from 2008 and the partial skeleton from the museum, could belong to the same individual animal, and that they were related to Spinosaurus. Following these observations, scientific cooperation expanded beyond a single institution. An international group of researchers began working together to study the fossils in more detail. Nizar Ibrahim became part of this collaboration along with other paleontologists from different countries. The fossils that were held at the Museo di Storia Naturale di Milano were transferred for detailed analysis to the University of Chicago, where further preparation and scientific examination were carried out. This step allowed researchers to use additional laboratory methods and comparative studies to better understand the anatomical structure of the remains. In the year 2013, Nizar Ibrahim worked together with Moroccan paleontologist Samir Zouri and British paleontologist David Martil. They travelled to the city of Casablanca in order to locate the original fossil dealer who had been involved in the chain of fossil acquisition. After searching, they were able to identify and find this dealer. Once contact was made, the dealer agreed to guide them back to the original site where the fossils had been discovered. This step was important because it allowed the researchers to directly observe the geological location from which the bones had been removed. At the site, further excavation and fieldwork took place over a period of several years. During this extended work, additional fossil material belonging to a subadult individual was recovered. The recovered skeleton included parts of the skull, which were fragmentary and incomplete, along with several vertebrae from different sections of the spine, including cervical vertebrae from the neck region, dorsal vertebrae from the back, and caudal vertebrae from the tail. Neural spines were also present among the remains, along with a complete sacrum, which is the fused set of vertebrae connecting the spine to the pelvic region. A large portion of the hind limbs was recovered, providing information about the structure of the legs. Several bones from the feet, known as pedal phalanges, were also found, along with multiple dorsal ribs that helped reconstruct part of the rib cage. This collection of bones formed a more complete understanding of the individual animal than earlier fragmentary finds had allowed. The fossils were discovered within geological layers belonging to the Douria Formation, which is part of the larger Kem beds in southeastern Morocco. The specific locality is in the region of Dra Tafilalet, near the area of Zrigat. These geological formations date back to the Cenomanian stage of the mid-Cretaceous period, which places them tens of millions of years into the past in Earth's geological history. After recovery, the fossils were transported and stored at the museum in Casablanca under the specimen number FSAC KK 11888, where they were catalogued and preserved for further scientific research. In the year 2014, Nizar Ibrahim and his colleagues published a scientific interpretation of the fossils. They assigned the material to the species Spinosaurus aegyptiacus. They also proposed that this specimen should serve as a neotype, meaning a replacement reference specimen for the species. In their interpretation, they suggested that all spinosaurid fossils from the Cenomanian deposits of North Africa should be grouped under this same species classification. Their description of the fossils included interpretations of body structure that suggested unusual proportions, including relatively short hind limbs and a body plan that appeared different from earlier reconstructions of Spinosaurus. This interpretation led to wide scientific attention and discussion. The proposal and interpretation generated significant scientific discussion among paleontologists. Some researchers examined the body proportions of the specimen carefully, especially focusing on the hind limbs, which appeared shorter in proportion than in earlier studied materials. These differences led to detailed analysis of whether the fossil represented a single individual or whether it might be a mixture of bones from different sources. Multiple paleontologists studied the material and provided arguments that the specimen was not a chimera, meaning it was not composed of unrelated animals mixed together. Instead, they supported the idea that the bones belonged to a single Spinosaurus individual, while also noting that the proportions suggested a different understanding of hind limb size than previously assumed. In the year 2015, British paleontologist Sir Joshua Evers, together with other colleagues, reviewed the proposal that FSAC KK 11888 should serve as a neotype. They expressed disagreement with this designation. Their analysis focused on several points, including the lack of complete association data for the fossils, uncertainty about the exact locality context of the specimen, and differences in anatomical details when compared with the original Spinosaurus material described by Ernst Stromer. They also discussed geographical separation between the original holotype site and the location where FSAC KK 11888 was found. Based on these factors, they argued that the requirements for assigning a neotype were not fully satisfied according to the rules of zoological classification. They further suggested that the fossil material might be more consistent with another named species, Spinosaurus maroccanus, rather than Spinosaurus aegyptiacus, and therefore questioned the need for redefining the species using this specimen. Additional scientific interpretations also emerged regarding the structure of the skeleton. Some researchers studied the proportions of the dorsal vertebrae in relation to the limb bones and compared these measurements with other known spinosaurid fossils, including material informally referred to in research discussions as Spinosaurus B. These studies raised the possibility that FSAC KK 11888 might represent a combination of fossil elements from more than one individual, or that it might include remains that were not all from the same species. This interpretation focused on how different parts of the skeleton might have been assembled or associated during excavation and preparation stages. Between the years 2015 and 2019, further field expeditions were carried out at the original fossil site in Morocco. These expeditions resulted in the discovery of additional fossil material that expanded the known parts of FSAC KK 11888. Among the newly recovered remains were many caudal vertebrae which, together, represented a large portion of the tail, estimated at about 80% of its full length, with a preserved tail section measuring approximately 4 meters in length. Other recovered elements included additional parts of the feet, further hind limb bones, and more fragments of the skull. Some of these pieces were discovered during later excavation seasons, while others were identified from material that had been previously collected, but not fully recognized or classified during earlier work. By the year 2020, Nizar Ibrahim and his research team published a detailed description of the tail structure of FSAC KK11-888. Their analysis showed that the caudal vertebrae of this specimen closely matched those found in both the original holotype, described by Stromer, and other comparative specimens labelled as Spinosaurus material. This provided further information about the structure of the tail and its arrangement. The expanded fossil evidence collected during multiple field seasons allowed researchers to associate many of the recovered bones with a single individual specimen more confidently, based on consistent anatomical features observed across the material. The estimated body size of the specimen, excluding the full tail section, from the front part of the skull region to the rear part of the pelvic area, was measured at approximately 5.88 meters in length. The full tail length, based on reconstructed vertebrae, was estimated at approximately 5.3 meters. These measurements were derived from the assembled fossil elements and their anatomical proportions as interpreted during research analysis and reconstruction work carried out across multiple years of study and excavation activities. Since its discovery, Spinosaurus has been regarded as one of the largest known theropod dinosaurs, and from early scientific descriptions it has consistently been placed among the biggest predatory dinosaurs known from fossil records. In the year 1926, Friedrich von Huene included Spinosaurus in his review of very large theropods and considered it one of the most massive members of this group, estimating its body length at about 15 meters, which is about 49 feet, and its weight at more than 6 tons, which is about 6.6 short tons. In the year 1982, Donald F. Glut also placed Spinosaurus among the largest theropods in his survey work, again giving a similar estimated length of around 15 meters or 49 feet and a body mass of over 6 tons. These early estimates were based on limited fossil material and comparisons with better-known large theropods available at the time, and they reflected the general view that Spinosaurus belonged to the upper size range of predatory dinosaurs. In the year 1988, Gregory S. Paul also described Spinosaurus as one of the longest theropods, giving a length estimate of about 15 meters or 49 feet, but he proposed a lower body mass estimate of about 4 tons or 4.4 short tons. This difference in weight estimate compared to earlier authors showed how different approaches to body reconstruction could lead to different conclusions, even when similar length estimates were used. His work focused on skeletal proportions and overall body build, which led to a lighter interpretation of the animal's mass. In the year 2005, Cristiano Dal Sasso and colleagues re-evaluated the size of Spinosaurus by using comparisons with related spinosaurid dinosaurs, such as Suchomimus. They assumed that Spinosaurus and Suchomimus shared similar body proportions relative to skull size, and they used skull measurements to estimate total body length. Based on this method, they suggested that Spinosaurus could have reached a length between 16 meters and 18 meters, which is about 52 feet to 59 feet, and a body mass between 7 tons and 9 tons, which is about 7.7 to 9.9 short tons. Their method relied heavily on scaling relationships between skull size and total body size in related dinosaurs, which was a common approach when full skeletons were not available. In the year 2007, François Terrien and Donald Henderson published a study that questioned earlier size estimates for Spinosaurus. They used skull length as the main scaling factor for estimating body size in theropod dinosaurs. Based on estimated skull lengths ranging from 1.5 meters to 1.75 meters, which is about 4 feet 11 inches to 5 feet 9 inches. They calculated that Spinosaurus had a body length between 12.6 meters and 14.3 meters, which is about 41 feet to 47 feet, and a body mass between 12 tons and 20.9 tons, which is about 13.2 to 23 short tons. They also compared these results with estimates for Suchomimus, assumed to be about 11 meters long or 36 feet, and calculated its body mass to be between 11.7 tons and 16.7 tons, which is about 12.9 to 18.4 short tons. Their findings suggested that smaller length estimates for Spinosaurus would place it below some other large theropods, such as Carcharodontosaurus and Giganotosaurus, based on mass and body structure. In the year 2020, Nicolas Campione and David Evans discussed limitations in using skull length as a direct predictor of total body size in dinosaurs. They pointed out that in some species, parts of the skull do not grow in a strictly proportional way with the rest of the body, especially the region in front of the eye sockets. They noted that in Spinosaurus and similar animals, different evolutionary pressures could have affected skull shape independently from overall body size, meaning that skull-based scaling could produce uncertain results. In the year 2014, Nizar Ibrahim and colleagues proposed that an adult Spinosaurus aegyptiacus could exceed 15 meters in length, which is about 49 feet. This estimate was based on a reconstruction of fossil material and comparisons with other spinosaurid remains. Later in the year 2022, Paul Serino and colleagues presented a different estimate based on a three-dimensional skeletal model created using computed tomography scans. In their model, the vertebral column was positioned in a neutral alignment, and they estimated that Spinosaurus aegyptiacus reached a maximum length of about 14 meters, which is about 46 feet, and a maximum body mass of about 7.4 tons, which is about 8.2 short tons. They argued that earlier graphical reconstructions may have increased certain body proportions, including the length of the spinal column by about 10%, the depth of the rib cage by about 25%, and the length of the forelimbs by about 30%, compared to measurements taken directly from scanned fossils. They also explained that these changes could shift the calculated center of body mass forward when applied to a reconstructed flesh model, affecting overall size interpretation. The skull of Spinosaurus was long and narrow, with a snout filled with straight, cone-shaped teeth that did not have serrated edges. On each side of the front part of the upper jaw, known as the premaxillae, there were about 6 or 7 teeth. Behind these, in the maxillae, there were about 12 additional teeth on each side. The second and third teeth in the premaxilla on each side were noticeably larger than the other front teeth. This created a gap between these enlarged front teeth and the larger teeth located further back in the maxilla. Large teeth in the lower jaw would fit into this gap when the mouth was closed. The tip of the snout, which held the largest front teeth, was widened compared to the rest of the snout, and a small raised structure was present in front of the eyes. Different studies have estimated skull length based on fossil specimens such as MSNM V4, 047, UCPC-2, and BSP 1912-819. In the year 2005, Dal Sasso and colleagues estimated that an adult Spinosaurus skull could reach about 1.75 meters, which is about 5.7 feet, based on comparisons with related species and assumptions about skull shape. In the year 2016, Hendricks and colleagues suggested a slightly smaller estimate of about 1.6 meters, which is about 5.2 feet. For a younger individual known as a subadult neotype specimen, the skull length was estimated to reach up to about 1.12 meters, which is about 3.7 feet. As a member of the Spinosaurid group, Spinosaurus had a long and muscular neck that curved in an S-shaped form. The shoulder region was strongly developed and the forelimbs were large and robust, each ending in 3 clawed fingers. The first finger, often referred to as the thumb, was the largest of the 3. The bones in the fingers were elongated and the claws were only slightly curved compared to those of many other theropods. This structure suggests that the hands were relatively long in proportion to the forelimbs when compared with other related dinosaurs. Along the back of Spinosaurus were very tall extensions of the vertebrae called neural spines. These spines formed a prominent structure commonly referred to as a sail. In some parts of the back, these spines were more than 10 times taller than the diameter of the vertebral body from which they extended. The spines were slightly longer, from front to back at their base, and became narrower toward the top. Their structure was different from the thin rod-like spines seen in some earlier prehistoric animals, such as Dimetrodon and Edaphosaurus, and also different from the thicker spine structures seen in some iguanodontian dinosaurs, such as Uranosaurus. Other dinosaurs, including Uranosaurus, from the same general region and time period, and the sauropod Amargasaurus from South America, also developed elongated neural spines, but their structures were not identical to those of Spinosaurus. These features may have developed independently in different groups through separate evolutionary processes. In earlier scientific interpretations, such structures were sometimes compared with those of older synapsids, such as Dimetrodon, which lived long before dinosaurs appeared, but later studies emphasized differences in structure and development. Some researchers suggested that the spinal structure of Spinosaurus may not have functioned as a thin sail, but instead may have formed a thicker, hump-like structure. In the year 1915, Ernst Stromer suggested that the neural spines could have supported a large mass of tissue, possibly including fat deposits. In the year 1997, Jack Bowman Bailey also supported the idea that the structure may have been more hump-like, based on comparisons with other animals that have elongated vertebral spines. Bailey argued that in Spinosaurus and related dinosaurs such as Uranosaurus, the spines were relatively shorter and thicker than those of animals known to have true sails, and he compared them to the spinal structures of large mammals such as Megacerops and bison latifrons. In the year 2014, Ibrahim and colleagues proposed that the spines may have been covered tightly by skin, based on their shape, compact arrangement, and limited evidence of strong blood vessel development. Spinosaurus also had a pelvis that was smaller than those of most other large theropod dinosaurs, with the ilium reduced to about half the surface area seen in many related species. The hind limbs were relatively short, measuring just over 25% of the total body length. The tibia was longer than the femur, which is different from the usual condition seen in many theropods. The first toe, also called the hallux, touched the ground and the toe bones were long and strongly built. The ends of the toes had flattened claws, which suggest adaptation for walking on unstable surfaces, and there is evidence that the feet may have had webbing between the toes. The tail of Spinosaurus had elongated neural spines extending from the caudal vertebrae, along with long chevron bones on the underside of the tail. These features created a tall and narrow tail structure. The shape of the tail has been described as paddle-like or fin-like in form, and it resembles the tail structure seen in some modern animals, such as crocodilians and newts, based on bone arrangement and proportions. Spinosaurus is recognized as the main name genus used to define several major taxonomic groups within a broader set of carnivorous dinosaurs known from fossil evidence. It serves as the type genus for a family-level grouping known as Spinosauridae, and it also forms the basis for the naming of a subfamily called Spinosaurini, as well as a more restricted tribe-level grouping known as Spinosaurini. These classifications are based on anatomical characteristics observed in fossil skull material, teeth, and vertebrae, as well as phylogenetic analysis of evolutionary relationships among related theropod dinosaurs. The subfamily Spinosaurini includes several named genera that have been identified from fossil remains across different continents and geological formations. Among these are Oxalia and Sigilmassasaurus, both of which have been considered in some research discussions as potentially representing the same biological genus as Spinosaurus, based on similarities in fossil material, although separate naming has also been used in other interpretations of the fossil record. The subfamily also includes Irritator, a genus identified from cranial remains preserved in Cretaceous rock layers, and Angaturama, which is sometimes treated as representing the same biological taxon as Irritator, based on overlap in known skull fragments and anatomical structure. Additional genera sometimes placed within Spinosaurini include Ichthyovenator, which has been identified from the partial skeletal remains, and Siamosaurus, known mostly from isolated teeth discovered in sedimentary deposits. Another genus sometimes discussed in relation to this group is Camarillosaurus, which has been examined in phylogenetic studies exploring its placement among theropod lineages. The tribal grouping Spinosaurini is defined in systematic terms as including those spinosaurid dinosaurs that share a set of evolutionary relationships associated with Spinosaurus aegyptiacus and related forms, identified through skeletal and cranial characteristics observed in fossil specimens. Diagnostic anatomical features used in defining this group include the structure of the premaxilla, which in included taxa tends to show elongation, and the configuration of the external narial opening, where the premaxilla contributes differently in placement and structure when compared with other spinosaurid forms such as Irritator and Oxalia. These features are recorded through fossil skull analysis and comparative anatomical reconstruction of preserved cranial elements. The broader family Spinosauridae was first established in early paleontological classification work by Ernst Stromer, who initially created the group specifically for Spinosaurus, based on fossil discoveries from North African geological formations. Stromer observed anatomical structures in the teeth, vertebrae, and jaw bones that differed from many other theropod dinosaurs known at the time. These structures included elongated neural spines in the vertebral column and distinctive tooth shapes preserved in fossil fragments. Stromer's classification placed Spinosaurus in a separate grouping among theropods based on these anatomical observations. Early interpretations of evolutionary relationships suggested possible connections between Spinosaurus and other theropods, such as Dryptosaurus and Tyrannosaurus. These suggestions were based on limited fossil comparisons available at the time, particularly when examining fragmentary remains. Stromer also considered fossil genera, such as Streptospondylus and Antrodamus, which is currently recognized under the name Allosaurus. These references were part of early attempts to interpret the evolutionary position of Spinosaurus, using incomplete fossil evidence. During the early to mid-20th century, from the 1920s through the 1980s, the classification of Spinosaurus was often placed within broader theropod groupings such as Megalosauridae or Carnosauria. These classifications reflected the limited understanding of Spinosaurid diversity during that period. The fossil remains available were fragmentary, and interpretations relied heavily on partial skeletal structures. In some studies, large theropods with elongated neural spines, such as Acrocanthosaurus and Altispinax, were also considered in relation to Spinosauridae based on the presence of tall neural spines along their vertebrae. These interpretations were later re-evaluated in subsequent research. Later phylogenetic studies re-examined these relationships using more complete fossil data and refined analytical methods. These studies placed Acrocanthosaurus within Carcharodontosauridae and also within the broader clade Allosauroidea. Similar reassessments applied to Altispinax, which was also placed within related allosauroid groups in later classification frameworks. In the year 1986, research by British paleontologists Alan Charig and Angela Milner described Baryonyx based on fossil material discovered in England. They assigned it to a distinct family-level grouping named Baryonychidae due to its unique skeletal features, particularly in the skull and forelimb structure. In subsequent analysis in 1988, American paleontologist Gregory S. Paul discussed similarities between Baryonyx and Spinosaurus, focusing on skull morphology such as the shape of the snout and the arrangement of teeth. In 1989, Buffetot expanded on these interpretations and described relationships among spinosaurid dinosaurs, focusing on feeding ecology and cranial features. The study emphasized similarities in skull construction and tooth form between Baryonyx and Spinosaurus, particularly in relation to elongated snouts and conical teeth adapted for capturing aquatic prey. These interpretations contributed to increasing recognition of a broader group of related spinosaurid dinosaurs distributed across multiple continents. Additional fossil discoveries during the late 20th century expanded knowledge of spinosaurid diversity. The identification of Irritator, Angatorama, and other related fossil material contributed to the recognition of spinosaurid presence across both northern and southern hemispheres. These findings supported the understanding of a widespread group of theropod dinosaurs distributed across ancient landmasses during the Cretaceous period. In 1998, Paul Serino and colleagues described Suchomimus from fossil material found in Niger. Their research included a broader phylogenetic framework for spinosaurid dinosaurs, in which the group Spinosauridae was placed within a larger superfamily level grouping sometimes referred to as Spinosauroidea, which is now generally treated within Megalosauroidea. In this framework, spinosaurids were defined as those theropods more closely associated with Spinosaurus aegyptiacus than with Torvosaurus tanneri. Within this grouping, two main subdivisions were identified, Baryonychinae and Spinosaurinae. In this classification framework, Baryonychinae included genera such as Baryonyx and Suchomimus, while Spinosaurinae included Spinosaurus and Irritator. In 2004, further refinement of this classification was provided by Thomas Holtz and colleagues, who defined Spinosaurinae as including those spinosaurids sharing a closer evolutionary relationship with Spinosaurus aegyptiacus than with Baryonyx walkeri. This definition was based on cranial and dental features, including tooth spacing and tooth shape patterns observed in fossil skulls. Spinosaurine dinosaurs are characterized by certain dental structures that include straight, unserrated teeth arranged with noticeable spacing along the jaw. In some specimens, around 12 teeth are present on one side of the upper jaw. These features are observed in taxa, such as Spinosaurus and Irritator. In contrast, baryonychine dinosaurs, such as Baryonyx and Suchomimus, possess curved teeth that include serration patterns and higher tooth counts along the jaw, with some specimens showing around 30 teeth on one side of the upper jaw. These anatomical details are used in phylogenetic analysis to interpret relationships within Spinosauridae. From the 1990s onward, Spinosaurid fossils have been identified in geological formations dating to the Cretaceous period and in some cases possibly extending into Jurassic deposits. These fossils have been discovered in regions across Africa, Asia, Europe and South America, indicating a wide geographical distribution of Spinosauridae. African fossils include those related to Spinosaurus. Asian fossils include genera such as Siamosaurus. European fossils include forms such as Baryonyx, and South American fossils include genera such as Irritator and Oxalia. Phylogenetic analyses of Spinosauridae have continued to refine the relationships among its members. Many studies consistently place Spinosaurus in close association with genera such as Irritator and Oxalia. The subfamily Baryonychinae commonly includes Baryonyx and Suchomimus in many analyses. Research published in 2017 by Brazilian paleontologist Marcos Sales and colleagues examined South American Spinosaurid fossils, including Angaturama, Irritator, and Oxalia. This analysis considered cranial and dental characteristics and produced interpretations in which these taxa occupy positions between the broader groupings associated with Baryonychinae and Spinosaurinae. These interpretations influenced subsequent revisions of Spinosaurid classification, including discussions of monophyly and subgroup structure within Spinosauridae. Later phylogenetic work involving Paul Serino and colleagues included updated matrices, analyzing relationships of Spinosaurus mirabilis. This work incorporated revised datasets and fossil character scoring methods to evaluate its placement within Spinosaurus. The analysis recovered consistent grouping patterns linking the Nigerian taxon with Spinosaurus aegyptiacus, supporting assignment within the same genus framework used in current systematic interpretations of Spinosauridae. The large raised structure along the back of Spinosaurus, often described as a sail or hump, has an uncertain purpose, and researchers have suggested multiple possible explanations based on fossil evidence, comparisons with living animals, and physical reasoning. One major idea is that this structure may have been involved in controlling body temperature. Another idea is that it may have been used for visual display. It has also been suggested that such a tall and noticeable feature on the animal's back could have made the animal appear even larger than its actual size, which may have influenced how other animals reacted to it during encounters, especially in situations involving competition or territorial behavior. The idea of temperature control is one of the most widely discussed explanations. If the sail or hump contained many blood vessels, warm blood flowing through it could have helped the animal interact with environmental heat more directly. With a large surface area exposed to air, the structure could have allowed heat from the environment to enter the body when conditions were cooler. This would suggest that the animal might not have maintained a fully constant, high internal body temperature at all times, but instead may have had a mixed form of temperature regulation that depended partly on external conditions. In environments where night temperatures dropped significantly, or where cooler periods were common, such a structure could have helped the animal take in warmth more efficiently during those times. At the same time, the same structure could also have worked in the opposite direction, by helping the animal release excess heat from its body. Large animals face a particular challenge in controlling heat because their body size increases much faster in volume than in surface area. This means that heat produced inside the body does not easily escape through the skin. In physical terms, as body size increases, the ratio between surface area and volume becomes smaller, which makes it harder for heat to leave the body efficiently. This creates a situation where overheating can become a greater problem than warming up. A large sail or hump would increase the total surface area of the body without greatly increasing its volume, allowing more space for heat exchange with the surrounding air. If the animal positioned this structure in a way that reduced direct exposure to strong sunlight, or if it oriented the sail so that airflow passed across it from the sides, then heat could be removed more effectively. In warm environments, air movement across the surface would assist in carrying heat away from the body. This idea suggests that the sail may have functioned in both directions, depending on environmental conditions, helping the animal either absorb heat or release it as needed. However, not all researchers agree with the idea that the structure was mainly for heat control. Another interpretation suggests that instead of being primarily a thin, blood-rich sail, the structure may have been a fatty hump. In this interpretation, the raised area would have stored energy in the form of fat, which could be used during periods when food was less available. Fat storage would also provide insulation, helping to reduce sudden changes in body temperature. In addition, a fatty hump could have offered protection against overheating by acting as a buffer between the internal organs and external heat. This idea was suggested by Bailey in the year 1997, who argued that the structure might have absorbed more heat than it released if it were thin and heavily vascularized, making a fatty composition more likely. Another proposed explanation focuses on communication and mating behavior. Many modern animals have large or unusual body structures that are used during courtship and social interactions. These structures can be used to attract mates or to signal strength and health to other members of the same species. In this context, the sail of Spinosaurus may have been used as a visual signal during mating behavior. A tall and noticeable structure on the back could have been useful in attracting attention during courtship displays. Early researcher Stromer suggested that there may have been differences in the size of the neural spines between males and females, which would support the idea that the structure played a role in reproduction and mate selection. A different line of research developed in the year 2015 by Gimser and colleagues proposed a hydrodynamic function for the sail. In this interpretation, the structure may have influenced movement through water rather than air. The sail is compared to the dorsal fins of sailfish, which are modern, fast-swimming fish that use large dorsal fins during hunting. In Spinosaurus, the bones supporting the sail, known as neural spines, form a shape that is more rectangular than in earlier related animals, which had more rounded or crescent-shaped structures. This difference in shape has been used to suggest that the sail in Spinosaurus may have had a specialized function in aquatic movement. In this hydrodynamic interpretation, the sail may have helped stabilize the body while moving through water. When moving sideways or turning sharply, large animals experience rotational forces that can affect balance. A vertical structure like a sail could resist some of these forces by interacting with water flow along the body. This stabilizing effect could reduce unwanted turning movements during rapid motion in water. It has also been suggested that the sail could have worked together with the tail and neck during hunting behavior. The tail of Spinosaurus is long and narrow, and some researchers have compared it to the tail of modern thresher sharks. Thresher sharks use their tails to strike groups of fish, stunning them before feeding. In a similar idea, Spinosaurus may have used its tail to strike or disturb groups of prey in water. When fish gather in dense groups, they sometimes form tight clusters known as bait balls. These bait balls make it easier for predators to target multiple prey in a small area. However, forming such a dense group often requires pressure from predators or coordinated hunting behavior. In modern marine animals such as sailfish, hunting behavior can involve the use of multiple body parts at the same time. Sailfish sometimes raise their dorsal fins while circling groups of fish, which helps make them appear larger and may influence the movement of the prey. During rapid movements, the dorsal fin and body work together to maintain stability in the water. When the sailfish makes quick movements with its snout through groups of fish, its fins help maintain balance and control, improving precision. It has been suggested that similar principles could have applied to Spinosaurus, where the sail may have helped stabilize the body during rapid movements of the head and tail. In this type of interpretation, the sail would reduce rotational movement of the body when the animal moved its tail or neck quickly from side to side. This reduction in rotation would make movements more controlled and efficient. Some researchers have also suggested that the presence of a large sail could make it harder for prey to clearly interpret the full shape of the approaching predator, since parts of the body may appear separated or less clearly defined in water conditions where visibility is limited. Further ideas combine multiple functions into a single interpretation of behavior. In this view, Spinosaurus may have used its sail to help gather prey into concentrated groups, while also using its tail and neck to strike or injure prey once they were close together. The sail, when submerged, could have acted as a stabilizing structure during strong sideways movements of the tail and neck. This stabilizing effect would help balance forces created by rapid movement in water, especially during sudden strikes. Some researchers suggest that smaller dorsal fins or reduced structures in other animals may allow easier access to water around the body for slashing movements, but may provide less stability during such actions. In contrast, a larger sail would increase stability, but also change how water flows around the body. This balance between movement efficiency and stability has been used to explore how Spinosaurus might have moved in aquatic environments. The sail may also have functioned as a central stabilizing point for the body during swimming. When the neck or tail moved strongly to one side, the sail could help counterbalance those movements and reduce unwanted tilting. This interaction between different parts of the body may have allowed more controlled movement in water, especially during fast swimming or sudden directional changes. The structure may also have played a role in supporting muscular development in the chest and neck region. Some researchers have noted that fossil evidence suggests strong muscle attachments in these areas, which could be related to powerful movements of the head and neck during feeding behavior. The combination of a strong neck, a long tail, and a tall dorsal structure may have influenced how forces were distributed across the body during motion in water. All of these interpretations remain based on anatomical evidence and comparisons with living animals, and each explanation focuses on different possible uses of the sail or hump, including temperature control, energy storage, visual signaling, and movement in water during hunting behavior. It is not clearly known whether Spinosaurus mainly lived as an animal that hunted on land or whether it mainly fed on fish, and this uncertainty comes from its long snout, its conical-shaped teeth and its nostrils being placed high on the skull, These features have often been used to suggest that it might have been adapted for catching aquatic prey, especially fish, but they do not give a single definite answer about its main feeding style. Ideas that Spinosaur-like dinosaurs focused on fish eating were already suggested earlier, for another related dinosaur called Baryonyx, by A.J. Charig and A.C. Milner. Their suggestion was based on body features that resemble those of crocodile-like animals, along with the discovery of fish scales that had been partly broken down by stomach acid inside the rib cage of a specimen that represents the original example used to define that species. In environments where spinosaurid dinosaurs lived, there were large fish present, including Morsonia, which lived in parts of northern Africa and South America during the middle part of the Cretaceous period. Evidence about diet in related dinosaurs from Europe and South America provides additional information. In Baryonyx, fish scales and bones from young iguanodon were found in the stomach area, showing that it did not rely on only one type of food. There is also evidence from a tooth found stuck in the bone of a pterosaur in South America, which shows that Spinosaur-related dinosaurs sometimes attacked flying reptiles as well. Because of this variety of evidence, Spinosaurus has often been described as an animal that did not depend on a single food source, but instead took different kinds of available prey depending on opportunity, including fish, small land animals, medium-sized animals, and also dead animals it found. Some researchers have suggested that it may have behaved in a way similar to large modern bears in terms of feeding variety, especially in how it sometimes relied on water sources for food while also feeding on land-based animals and scavenged remains. Inside the structure of the snout, some researchers propose that Spinosaurus may have had special sensory structures capable of detecting movement in water. This idea suggests that it could have kept its snout close to the water surface and detected swimming animals without needing to rely heavily on sight. A study published in the year 2013 by Andrew R. Cuff and Emily J. Rayfield examined the mechanical properties of the skull and concluded that Spinosaurus was not restricted to eating only fish. Instead, its diet likely changed depending on the size of the individual animal, meaning younger or smaller individuals may have eaten different prey compared to larger ones. The shape of the front part of the skull allowed it to resist bending up and down, but it was not strong in resisting sideways pressure when compared with some related animals like Baryonyx or modern crocodilians. This suggests that while fish may have been an important part of its diet, it could also have taken other animals when the opportunity appeared. In the year 2022, Sakamoto estimated that Spinosaurus had a bite force at the front of the jaws of 4,829 newtons, and at the back of the jaws about 11,936 newtons. Based on this, it was suggested that its jaws were more suited for closing quickly rather than applying long crushing pressure. This type of jaw action indicates that it may have captured prey using fast movements rather than slow, forceful bites, a method that is often seen in animals that feed partly in water environments. A study published in the year 2024 proposed that Spinosaurus and other closely related Spinosaurian dinosaurs did not only eat fish, but also fed on small and medium-sized animals that lived on land. This study also suggested that their bite strength was relatively weak when compared with many other large predatory dinosaurs, meaning they may have relied more on catching easy prey rather than overpowering large, strong animals. An earlier study from the year 2010 by Romain Amiot and colleagues examined oxygen isotope patterns in the teeth of spinosaurid dinosaurs, including Spinosaurus. These chemical patterns were compared with those of other animals from the same environments, including crocodilians, turtles, and other predatory dinosaurs, such as Carcharodontosaurus. The results showed that the oxygen isotope values in Spinosaurus teeth from 5 out of 6 locations were more similar to those of animals that spent much of their time in water, such as turtles and crocodiles, than to those of other land-based predators. This suggested that Spinosaurus likely spent a significant amount of time in aquatic environments. The researchers proposed that it may have moved between land and water environments in order to access food and reduce competition with other large predators. However, a study published in the year 2018 by Donald Henderson challenged the idea that Spinosaurus could live comfortably in water. By examining how lungs function in crocodiles and comparing them to the estimated lung structure of Spinosaurus, it was suggested that Spinosaurus would not easily sink or remain underwater. Instead, it would have stayed afloat and would likely have kept its head above the water surface. The study also suggested that the animal would need to continuously move its hind limbs in order to maintain balance in water, unlike modern semi-aquatic animals that do not require such constant movement. Based on this interpretation, it was proposed that Spinosaurus may not have been adapted for fully underwater hunting, and may have spent much of its time on land or in shallow water areas. Later research focusing on the tail structure of Spinosaurus provided a different interpretation. Studies carried out in the year 2018 by Ibrahim, Pierce, Lauder, Serino, and colleagues examined fossil remains of the tail and found that it had tall blade-like structures running along its length. These features suggest that the tail was adapted for movement in water. Experimental work comparing movement forces showed that the tail of Spinosaurus could generate significantly more forward motion in water than the tails of many land-based theropod dinosaurs such as Coelophysis and Allosaurus. It was also found to be more efficient at producing forward thrust. This evidence suggests that Spinosaurus may have been able to move through water for extended periods while hunting. In the year 2021, David Hone and Thomas Holtz published a study suggesting a different interpretation of Spinosaurus anatomy. They argued that the structure of the nostrils and eye sockets makes a fully water-based hunting lifestyle unlikely, because the position of these features would require the head to be lifted in a less efficient way for breathing at the water surface. They also noted that the body shape, including the long back structure and rigid trunk, would create resistance in water movement. They suggested that animals that actively hunt underwater typically have flexible bodies that allow quick turning movements, and they argued that Spinosaurus does not clearly show these features. In the year 2022, another study by Fabry and colleagues compared bone density in Spinosaurus, Baryonyx, and Suchomimus. The results showed that Spinosaurus and Baryonyx had heavier, denser bones, while Suchomimus had lighter bones with more internal spaces. This difference suggests that Spinosaurus and Baryonyx may have been better suited for moving underwater, while Suchomimus may have preferred shallow water environments rather than deeper ones. This study suggested that different Spinosaurid dinosaurs may have lived in different ecological conditions instead of all living in the same way. In the same year, a different study led by Serino and colleagues presented another interpretation. Their research used reconstructed digital models of the skeleton, including estimates of muscles and air spaces inside the body. Their findings suggested that Spinosaurus was mainly a bipedal animal when on land and would have been unstable and slow when swimming in deeper water. They also suggested that fossils indicate it lived not only near coastal areas, but also along rivers and lakes further inland. According to this view, Spinosaurus may have hunted by waiting for prey in water environments, rather than actively chasing it underwater. They also proposed that the tall tail structure may not have been used mainly for swimming, but could also have had other functions, since similar tall tail structures in modern animals are sometimes used for display. A study published in the year 2024 by Myhrvold and colleagues also questioned the idea of Spinosaurus being a diving predator. Instead, they suggested that its feeding behavior may have been more similar to that of wading birds that move through shallow water and catch prey near the surface rather than diving deeply. Another study from the same year examined skull measurements and found that the shape of the skull may be most similar to that of birds such as herons that hunt by standing in shallow water and striking quickly at prey. The researchers also noted uncertainty about whether the skull structure would be suitable for deep diving behavior. In a study published in the year 2026, Cow and colleagues examined several Spinosauran skulls. Their research found evidence suggesting the possible presence of salt-excreting glands similar to those found in some birds that live in water environments. This suggests that Spinosaurus and related dinosaurs may have been able to live and hunt in environments containing saltwater or mixed water conditions. However, the presence of these glands does not confirm whether these animals lived fully in water, hunted by diving, or used shallow water hunting methods similar to wading birds, leaving multiple interpretations still open within scientific discussion. The scientific understanding of the posture and movement of Spinosaurus has changed many times over the course of research history, especially as new fossils and interpretations have been introduced. In early scientific descriptions and reconstructions, this dinosaur was commonly presented as an animal that moved primarily using two legs, with its body supported by strong hind limbs and its forelimbs used for grasping or other functions not related to supporting body weight. This interpretation became widely accepted in many scientific discussions and museum displays for a long period of time, and it shaped how the animal was illustrated and understood in educational materials. During the middle part of the 20th century, different interpretations appeared in some scientific writings and artistic reconstructions, where the animal was sometimes shown using all four limbs to support its body weight on the ground. These interpretations did not become the dominant view, but were still present in scientific discussions and illustrations during that period. Some of these ideas were influenced by comparisons with other prehistoric animals known from fossils that had different body plans and limb structures, which encouraged researchers to explore alternative ways this dinosaur might have moved. In later decades, especially beginning around the middle of the 1970s, more attention was given to the possibility that members of the Spinosaur group, including Spinosaurus, might have used their front limbs to support themselves on the ground at least part of the time. This idea developed alongside discoveries of related dinosaurs that had strong and well-developed forelimbs. One of the important discoveries that influenced this thinking was the identification of Baryonyx, a close relative that had powerful arms and claws. The presence of such strong forelimbs in a related animal encouraged scientists to consider whether similar body mechanics might have been present in other members of the same broader group. At the same time, some researchers also began to consider how the weight and structure of certain parts of the body, including the tall structures along the back, that are often interpreted as sail-like or hump-like features, might have affected how the animal held itself on the ground. One scientific suggestion published in 1997 considered whether the weight distribution caused by these structures could have allowed or encouraged the use of the forelimbs in supporting the body during movement or resting. This idea led to artistic reconstructions that showed the animal placing weight on both the hind limbs and forelimbs in various positions. Studies of dinosaur limb structure also provided important information about how the hands of theropod dinosaurs functioned. Research showed that theropods, including members of the Spinosaur group, did not have the ability to rotate their forearms in a way that would allow the palms to face directly downward in a fully flat orientation. Even without this type of rotation, evidence from fossil trackways and preserved impressions from early Jurassic theropods showed that the hands could rest in a sideways orientation on the ground. This demonstrated that some degree of ground contact using the forelimbs was physically possible in certain positions, even if the hand structure limited the exact placement of the palm. These anatomical details became important in discussions about whether the animal could have used its forelimbs for supporting its weight during movement or resting. As research continued into the late 20th century, the idea of full-time ground movement using all four limbs for Spinosaurus gradually became less widely accepted in scientific literature. Even so, some researchers still considered the possibility that members of the Spinosaur group might have lowered their bodies and used both sets of limbs in specific situations, particularly when resting or moving in constrained environments. These ideas were influenced by ongoing studies of bone structure, joint movement, and muscle attachment patterns, which suggested that the animals had a combination of features not fully consistent with constant weight bearing on all four limbs during active movement on land. A major shift in interpretation occurred in the year 2014, when a scientific study led by Ibrahim and colleagues introduced new fossil material and revised reconstructions of Spinosaurus. This study presented a new view of the proportions of the hind limbs, suggesting that the legs were shorter than earlier reconstructions had indicated. The study also analysed the overall balance of the body and estimated the position of the centre of mass within the torso region. Based on these findings, the researchers proposed that movement on land using primarily the hind limbs might have been more difficult than previously assumed, and that the body structure could have supported the use of all four limbs when on land. The reconstruction presented in this study was created using fossil material from different individuals, with the goal of producing a complete body model by combining measurements from specimens of different sizes and scaling them to produce estimated full proportions of a single individual. Following the publication of this interpretation, several paleontologists reviewed the methods and conclusions. John Hutchinson of the Royal Veterinary College of the University of London expressed concern about the way different fossil individuals were combined to create a single reconstructed skeleton. He noted that combining separate specimens can introduce uncertainty in determining accurate body proportions. Scott Hartman also raised concerns regarding the scaling of the hind limbs and pelvic region, suggesting that the reconstructed proportions might not align with the measurements reported in the fossil descriptions. Hartman argued that certain parts of the body may have been represented with reduced length when compared with published data. On the other hand, Mark Whitten expressed agreement with the proportional interpretations presented in the study, supporting the view that the reconstructed body plan could reflect a realistic estimate of the animal's structure based on available evidence. Taxonomic studies also contributed to the discussion about movement and body structure. In the year 2015, Evers and colleagues published a revised analysis of Sigelmassasaurus, arguing that it represented a separate genus rather than being part of Spinosaurus. This interpretation introduced uncertainty regarding which fossils should be assigned to which genus, particularly in relation to the material used in earlier reconstructions. Because some fossil elements had previously been attributed to Spinosaurus but might belong to a different genus, questions arose about how body proportions should be interpreted when reconstructing posture and movement. Further biomechanical analysis was conducted in the year 2018 by Henderson, who evaluated the center of mass and overall balance of Spinosaurus using updated modeling techniques. This analysis suggested that the center of mass may have been located closer to the hip region than earlier studies had proposed. Based on this result, the study indicated that upright movement supported mainly by the hind limbs could have been mechanically feasible. This interpretation contributed to ongoing discussions about how the animal supported its body during movement on land and how weight distribution influenced posture. More recent work published in the year 2024 involved co-authorship by Sereno and other researchers, who reviewed earlier calculations of body balance and center of mass placement. This work stated that earlier modeling approaches used in some studies had positioned the center of mass farther forward in the body than appropriate based on revised data. After re-evaluating the calculations, the study suggested that Spinosaurus may have met the conditions associated with slow terrestrial movement, primarily supported by the hind limbs. This interpretation focused on the mechanical properties of movement and body support on land, based on updated mathematical modeling of skeletal structure and mass distribution. In addition to studies of adult individuals, fossil evidence from juvenile specimens has also contributed important information about development and behavior. An ungual phalanx measuring 21 millimeters, which is approximately 0.83 inches in length, was discovered and later described in the year 2018 by Simone Maganuco and Cristiano Dal Sasso. This bone belonged to a very young juvenile individual identified as CF, Spinosaurus aegyptiacus. The specimen was found in deposits dated to earlier research collections and is believed to represent an individual that would have measured approximately 1.78 meters in total length if scaled proportionally to adult body structure. This specimen provided information suggesting that adaptations associated with life in water or near water environments were present from a very early stage of development, possibly beginning at birth or shortly afterward, and remained present throughout the growth of the animal. The size of this specimen also made it one of the smallest known examples attributed to Spinosaurus. Additional fossil material attributed to Spinosaurus includes isolated teeth recovered from geological formations such as the Ifezuan Formation, one such tooth assigned to CF. Spinosaurus shows several distinctive structural features in its shape and surface. The tooth crown displays pronounced inward curvature along the inner surface of the tooth structure. There are 3 deep grooves extending from the region where the crown meets the root, continuing upward towards the upper part of the crown. The cutting edges of the tooth are reduced in extension and do not continue strongly toward either the tip or the base of the tooth. The tip of the tooth shows a worn surface, indicating interaction with material that caused abrasion during use. These dental features contribute to the broader understanding of feeding structures and functional adaptation in Spinosaurus, as they reflect specific anatomical characteristics preserved in fossil remains. The holotype specimen of Spinosaurus comes from the Bahariya Formation, which is one of several geological formations in North Africa that preserve fossils from the Cretaceous period. This formation is located in what is now Egypt and has produced important remains that help in understanding the presence of large dinosaurs in this region during that time. The holotype material represents the original set of fossils used to formally describe and define Spinosaurus as a species, and it remains an important reference point for later discoveries. Over time, additional fossils attributed to Spinosaurus have been identified in multiple other locations across North Africa, showing that the remains of this dinosaur are not limited to a single area or deposit. Spinosaurus fossils have been reported from several distinct geological sites beyond the Bahariya Formation. These include the Kem beds in Morocco, which are widely known for their rich fossil content, as well as the Farak Formation in Niger and the Eshkar Formation, also located in Niger. Additional remains have been found in the Gara Samani Formation in Algeria and in the Shanini sandstones, which are located in Tunisia. These widespread occurrences suggest that Spinosaurus lived across a broad region of northern Africa during the mid-Cretaceous period, and its fossils have been recovered from multiple sedimentary environments that once existed across this landscape. The distribution of these fossils also overlaps with that of other large theropod dinosaurs such as Bahariosaurus and Deltadromeus, which are also known from similar geological deposits in North Africa, although the classification and exact distribution of Deltadromeus and related forms are still matters of scientific discussion and ongoing research. During the time when Spinosaurus lived, North Africa was positioned along the northern edge of the African continent and was influenced by the nearby Tethys Sea. This large body of water played an important role in shaping the environment of the region. The land area that is now desert was then made up of environments that included coastal zones, river systems, and wetlands. Many of these areas contained mangrove-like vegetation, along with extensive tidal flats and networks of waterways. These conditions created a landscape that was often influenced by changes in water level, sediment movement, and seasonal flooding. The presence of such environments is supported by fossil evidence, preserved within the sedimentary layers of the formations where Spinosaurus remains have been discovered. The overall composition of dinosaur life in North Africa during this period shows an unusual pattern when compared with many other fossil-bearing regions from the same time. In many other places, herbivorous dinosaurs tend to be more diverse and numerous than carnivorous dinosaurs. However, in the fossil record of North Africa from this period, there are relatively fewer species of herbivorous dinosaurs compared to the number of carnivorous theropods. This unusual pattern has been referred to in scientific literature as Stromer's riddle, named after early researchers who first noted this imbalance in the fossil record. While some interpretations suggest that this pattern could be influenced by differences in fossil preservation or collection bias, continued discoveries from multiple formations continue to support the observation that theropod dinosaurs are particularly abundant in these deposits. The presence of many large carnivorous dinosaurs in the same ecosystems has led to interpretations involving ecological separation in their feeding habits and behavior. Different groups of theropods appear to have occupied different roles in the ecosystem, reducing direct competition for food resources. Spinosaurids, such as Spinosaurus, are thought to have focused more on aquatic prey, particularly fish and other water-dwelling organisms, based on anatomical features and associated fossil evidence. Other large theropods from the same formations are interpreted to have fed more heavily on land-dwelling animals, including herbivorous dinosaurs and other terrestrial vertebrates. Evidence supporting differences in diet among these groups includes isotopic studies, which analyze chemical signatures preserved in fossil bones. These studies have indicated that certain large theropods consumed a greater proportion of terrestrial animals in their diets, reflecting differences in feeding behavior among the dominant carnivorous groups. In this region during the mid-Cretaceous period, three major groups of large theropod dinosaurs are commonly recognized in the fossil record. These include members of Abelisauroidea, Spinosauridae, and Carcharodontosauridae. These groups are found together in several major fossil formations across North Africa, including the Kem beds, Eshkar Formation, Elrhaz Formation, and Baharia Formation. Their repeated presence across these formations indicates that these groups were widespread and played important roles in the ecosystems of the time. Within this context, certain theropods, such as Deltadromeus and Bahariasaurus, have been suggested to belong to abelisauroid-related groups. If this classification is correct, it would imply that these dinosaurs may have had feeding strategies different from other large carnivorous theropods, potentially including diets that incorporated a broader range of food sources. However, no skull material has been recovered for these genera, which limits precise understanding of their feeding behavior and ecological role. Fossils from the Baharia Formation, where the original Spinosaurus material was found, are preserved in sediments that represent tidal flat environments. These deposits contain fossilized plant material, including leaves and root systems, which indicate the presence of vegetation in the form of mangrove-like ecosystems dominated by seed ferns such as Weichselia reticulata. Alongside Spinosaurus, other theropod dinosaurs from this formation include Tamariraptor and Bahariasaurus, which represent part of the diverse carnivorous fauna of the region. Large herbivorous dinosaurs are also present in the formation, including sauropods such as Paralititan and Egyptosaurus, with Paralititan being one of the largest known animals from this environment. Earlier interpretations suggested that the Baharia Formation and the Kem beds shared very similar faunal compositions, although later studies have suggested that this similarity may require further detailed examination and reassessment. The Baharia Formation also contains evidence of other carnivorous dinosaurs, including abelisaurids, that likely lived in terrestrial environments and fed on other land-based animals. In addition to dinosaurs, the formation preserves a wide variety of other vertebrates and aquatic organisms. A fragmentary wing bone belonging to a pterosaur, possibly related to Anhanguera, has been discovered in these deposits, showing that flying reptiles were also part of this ecosystem. The aquatic fauna is especially diverse, including large fish such as Morsonia and Paranogmius, soar skates such as Onchopristis and Schizohyza, and sharks such as Squalicerax and Cretalamna. A variety of invertebrate fossils are also present, indicating rich aquatic biodiversity. Crocodilomorph reptiles are also known from the formation, including Stomatosuchus and Lebicosuchus, which represent different ecological roles within the freshwater and coastal environments. The Kem beds represent another major fossil-bearing region in North Africa, where Spinosaurus remains have been discovered. This geological unit is divided into three formations known as the Gara-Spar Formation, the Duria Formation, and the Izephuan Formation. Fossils attributed to Spinosaurus are mainly found in the latter two formations. Chemical analysis of isotopes from fossils of large theropods, such as Carcharodontosaurus and Spinosaurus, suggests that the climate of the Kem region experienced seasonal rainfall patterns, including periods resembling monsoon-like conditions rather than constant rainfall throughout the year. These climatic conditions are similar in some ways to those found in modern tropical and subtropical regions of parts of Africa and Southeast Asia. The environment of the Kem beds included river systems that carried fresh water, as indicated by the presence of lungfish and other freshwater organisms. The landscape contained a variety of environments, including river channels, riverbanks, sandbars, and floodplain areas. Fossils of large fish are common in these deposits, including species such as Onchopristis, Axelrodicthys, and Bawitius. Crocodiliform reptiles are also abundant, including species such as Lagonosuchus, Hermatosuchus, and Elosuchus, which represent different ecological roles within aquatic and semi-aquatic environments. Pterosaurs are also well represented, including toothed forms such as Sirocopteryx and Nycorhynchus, as well as toothless forms such as Elanca and Leptostomia, indicating a diverse group of flying reptiles living in or near these river systems. Dinosaur fossils from the Chem-Chem beds include both herbivorous and carnivorous groups, although herbivorous dinosaurs are relatively rare in comparison to carnivores. Sauropod dinosaurs are represented by species such as Rybachisaurus, along with indeterminate titanosauriform remains and other titanosaurs, some of which reached very large body sizes similar to Paralititan. Ornithischian dinosaurs are extremely uncommon in these deposits, with evidence limited to isolated teeth and fossil footprints that may belong to ornithopod dinosaurs, similar or in form to Iguanodon. Theropod dinosaurs are much more diverse in this region and include Spinosaurus, Sigilmatosaurus, if it is considered valid, and possibly other spinosaurid forms. Abelosaurid remains are also present, but often fragmentary, and Carcharodontosaurids, such as Carcharodontosaurus and Sauroniops, are known, although the classification of some of these remains is uncertain. Noasaurid fossils are also present, but are typically incomplete. Many of these fossils consist of isolated bones or partial skeletons, and their classification remains under ongoing study due to the limited nature of the preserved material. The role of Spinosaurus in its ecosystem as a major predatory animal can be understood through the study of its physical structure, its feeding behavior, its movement in water and on land, and the way it interacted with other living organisms in its environment during the middle part of the Cretaceous period. This animal lived in regions that are now part of North Africa, especially in areas that were once filled with rivers, swamps, and flowing water systems. These environments supported many kinds of fish, smaller reptiles, early crocodile relatives, and other dinosaurs that lived near water sources. In such settings, Spinosaurus occupied a position as one of the main large predators that relied heavily on aquatic and semi-aquatic food sources, shaping the distribution and survival of many animals that shared the same habitat. The body of Spinosaurus shows many features that supported its role as a predator that could operate in water environments. Its jaws were long and narrow, filled with conical teeth that were suitable for catching slippery prey, such as fish. These teeth were not designed for chewing, but for holding and gripping prey securely. The shape of the skull allowed it to quickly move its head into water to capture animals moving through rivers or shallow channels. The nostrils were placed higher on the skull, allowing breathing while much of the head remained close to or within water surfaces. This placement of breathing openings supported long periods spent near water while searching for food. The skeleton of Spinosaurus also shows adaptations that allowed movement in water. The bones in some parts of the body were dense, which helped with stability in aquatic environments. The tail structure was adapted in a way that supported movement through water, allowing it to push forward while swimming. The limbs, especially the hind limbs, were not primarily built for long land movement, but could still support movement on muddy or soft ground near river banks. The front limbs were strong and carried large claws, which may have been used for grasping prey near the water edge or within shallow water. The environment where Spinosaurus lived included wide river systems that carried water across large floodplains. These rivers supported many fish species that moved through channels and pools, creating a constant source of food for large predators. Spinosaurus likely spent a significant amount of time near these water bodies, using its sensory abilities to detect movement below the surface. The structure of its snout and teeth suggests that it could quickly snap at prey moving through water, reducing the chance of escape for smaller animals. The presence of Spinosaurus in this ecosystem influenced the behavior and distribution of other animals living in the same environment. Fish populations had to avoid areas where large predators were active, which affected their movement patterns within river systems. Smaller aquatic reptiles and early crocodile relatives also shared these environments, and they likely adjusted their behavior to reduce encounters with larger predatory animals. The feeding activity of Spinosaurus created pressure on aquatic life forms, shaping how they moved, fed, and reproduced within the ecosystem. On land near river edges, Spinosaurus interacted with other dinosaur species that visited water sources. These interactions included feeding on animals that came close to riverbanks, especially smaller dinosaurs or young individuals that were vulnerable while drinking or moving through shallow water. The ability to move between water and land allowed Spinosaurus to access food resources in both environments, although its body structure shows a stronger connection to aquatic life. The daily activity of Spinosaurus likely involved searching for food in water channels, resting near riverbanks, and moving slowly through shallow water areas. Its movement patterns were influenced by the availability of prey in different parts of the river system. Seasonal changes in water levels may have also affected how it moved through its habitat, with periods of high water expanding the areas where fish and other aquatic animals could be found. The skull of Spinosaurus provides important information about its feeding behavior. The elongated shape allowed it to cover a larger area when moving its head through water. The spacing of teeth helped reduce water resistance when snapping at prey. The jaw strength supported holding on to struggling animals, preventing escape once captured. These features together created an efficient system for catching aquatic prey in river environments. The sensory system of Spinosaurus likely supported its ability to detect movement in water. Small vibrations created by fish swimming or by other aquatic animals would have been important signals for locating food. The position of the eyes and nostrils allowed it to remain partially submerged while still observing its surroundings. This ability to remain still in water while detecting movement would have been useful in capturing fast-moving prey. The growth of Spinosaurus from juvenile stages to full size involved changes in feeding behavior and movement patterns. Younger individuals likely relied on smaller prey and may have stayed in shallower waters where food was easier to access. As they grew, their ability to handle larger prey increased, and they could access deeper or more active parts of river systems. This growth process contributed to the distribution of predation pressure across different sizes of aquatic animals within the ecosystem. The interaction between Spinosaurus and other large predators in the same environment also shaped its role. Other predatory dinosaurs and crocodile-like animals shared the same river systems, leading to a distribution of feeding areas based on available resources. Spinosaurus focused strongly on aquatic prey, which reduced direct overlap with animals that relied more heavily on land-based hunting. This distribution of feeding habits helped maintain balance in the ecosystem's structure of predator activity. The river systems where Spinosaurus lived also supported seasonal changes in water flow. During periods of high water, rivers expanded into surrounding floodplains, creating new feeding grounds for aquatic animals. Spinosaurus could move into these expanded areas, following fish and other prey into shallow waters. During lower water periods, animals became concentrated in deeper channels, increasing interaction between predators and prey. These cycles influenced feeding patterns and movement across the landscape. The feeding activity of Spinosaurus also affected the distribution of plant-eating animals that lived near water sources. Herbivorous dinosaurs that depended on rivers for drinking water had to remain cautious when approaching these areas. The presence of a large aquatic predator influenced where these animals chose to gather, often leading them to move in groups or select specific crossing points along rivers. The physical strength of Spinosaurus supported its ability to capture and control prey in water environments. The forelimbs equipped with large claws may have helped in holding on to struggling animals. These limbs could also assist in pulling prey closer to the body after capture. The coordination between jaws and limbs played an important role in ensuring successful feeding events. The long body structure and tail movement supported swimming ability that allowed Spinosaurus to move through water with control. This movement enabled it to follow prey through winding river channels and around obstacles such as submerged vegetation or rocks. The ability to move in different directions within water systems expanded its access to food sources across the ecosystem. The ecosystem itself contained many layers of life, including fish populations, aquatic reptiles, insects near water surfaces, and land animals visiting rivers. Spinosaurus interacted with multiple levels of this system through its feeding behavior. Its presence contributed to the regulation of fish numbers and influenced the behavior of other aquatic predators. This regulatory role affected how energy moved through the ecosystem, starting from aquatic plants and smaller organisms up to larger animals. The structure of riverbanks also played a role in shaping the behavior of Spinosaurus. Muddy edges, shallow pools, and slow-moving water sections provided suitable areas for hunting. These environments allowed it to approach prey with reduced movement detection. The interaction between water depth and prey availability influenced where feeding activity was concentrated within the ecosystem. The digestive system of Spinosaurus supported a diet focused on animals with soft bodies or bone structures that could be processed without heavy chewing. Fish bones, soft tissue, and small aquatic animals formed a significant part of its food intake. The processing of food within the body allowed energy to be extracted efficiently from aquatic prey sources. The reproductive behavior of Spinosaurus also influenced its role in the ecosystem. Nesting areas would have been located near water sources, allowing young individuals access to food shortly after hatching. The survival of young Spinosaurus depended on the availability of small prey in shallow waters. This connection between reproduction and aquatic environments strengthened its link to river-based ecosystems. The interaction between Spinosaurus and environmental changes, such as shifts in river paths or seasonal flooding, affected its distribution. As rivers changed course over time, feeding grounds would also shift, requiring movement to new areas. This adaptation to changing environments allowed it to remain present in regions where aquatic food sources were available. The presence of Spinosaurus within its ecosystem influenced the structure of aquatic communities. Fish species developed movement patterns that reduced exposure to shallow hunting zones. Other aquatic predators adjusted their activity times or locations to reduce overlap. These behavioral changes contributed to a complex network of interactions within river systems. The skull structure, limb proportions, and tail design all work together to support its role in capturing aquatic prey. These features allowed movement through water, detection of prey, and successful capture in environments where visibility and space could change rapidly. The integration of these physical traits supported continuous feeding activity in aquatic settings. The ecological presence of Spinosaurus remained closely connected to water systems throughout its life stages. From early growth to full development, its dependence on aquatic food sources shaped its behavior and movement. River systems provided both feeding opportunities and living space, allowing it to remain active across different parts of its habitat. The interactions between Spinosaurus and other organisms in its environment formed a complex network of feeding relationships. Aquatic prey species, land animals near water, and other predators all formed part of this system. The movement and feeding activity of Spinosaurus influenced how these organisms distributed themselves across the landscape, affecting patterns of survival and activity throughout the ecosystem. The structure of the ecosystem supported continuous cycles of feeding, movement, and reproduction involving many species. Within this system, Spinosaurus played a consistent role in aquatic predation, maintaining pressure on fish populations and interacting with other animals that depended on river systems for survival. The continued influence of Spinosaurus within its ecosystem can be further understood by looking at how its feeding activity shaped not only direct prey populations, but also the broader structure of life around river systems, floodplains, and shallow aquatic zones. Its presence in these environments meant that many animals living in or near water were constantly influenced by the possibility of encountering a large predator that could move between deeper channels and shallow edges. This constant presence created a stable pattern of avoidance behavior among smaller animals, especially those that depended on surface waters or river margins for feeding and movement. The fish communities in these river systems were likely among the most directly affected groups. Rivers in its environment contained many species of fish with different body shapes, swimming abilities, and feeding strategies. Some fish lived close to the bottom of rivers, while others moved in midwater or near the surface. Spinosaurus, with its long snout and conical teeth, was able to target fish across different depths, especially those that moved near the surface or within reach of its jaws during shallow water hunting. The repeated pressure of predation would have influenced fish behavior, encouraging schooling behavior in some species and more cautious movement near riverbanks. The aquatic reptiles and early crocodile relatives in the same environment also experienced strong ecological pressure from Spinosaurus activity. These animals often shared similar habitats, including slow-moving rivers, swamps, and floodplain channels. Some of these reptiles were smaller and more vulnerable, especially younger individuals. Spinosaurus likely fed on these animals when the opportunity arose, particularly when they were in shallow water or resting near the surface. The presence of a large predator would have affected where these reptiles chose to hunt or rest, leading them to use deeper or more concealed areas when possible. The structure of river ecosystems where Spinosaurus lived was not uniform but changed along its length and width. Some areas had strong water flow while others formed quiet pools or backwater zones. These different environments supported different types of prey. Spinosaurus likely moved through these zones depending on where food was most available. In slow-moving areas, fish and other aquatic animals were more concentrated, which increased feeding opportunities. In faster-moving sections, prey could escape more easily, but these areas still provided access to migrating fish and other moving animals. The physical design of Spinosaurus allowed it to take advantage of these varying environments. Its elongated body and tail helped it move through water with steady propulsion. This movement was not limited to straight paths, but included the ability to navigate curves and branching channels within river systems. This flexibility meant that it could follow prey into narrow or shallow areas, where other large predators might have had difficulty moving. The interaction between body structure and environment created a wide range of feeding opportunities across the ecosystem. The role of Spinosaurus also extended into how energy moved through the ecosystem. Energy in river systems began with aquatic plants and microscopic organisms, which were consumed by small fish and invertebrates. These small animals were then consumed by larger fish and aquatic predators. Spinosaurus, positioned at the upper level of this feeding structure, obtained energy by consuming these larger aquatic animals. This transfer of energy through multiple levels of the food system made it a key participant in controlling the flows of biological energy within its environment. The movement patterns of Spinosaurus likely followed predictable routes along river systems. These routes would have been influenced by prey density, water depth, and seasonal changes in river conditions. During periods when water levels rose, fish and other aquatic animals spread into new areas, and Spinosaurus could follow them into expanded floodplains. When water levels dropped, animals became concentrated in deeper channels, making hunting more focused but also more competitive among predators. The relationship between Spinosaurus and seasonal flooding cycles was especially important. Flooding events created temporary expansions of aquatic habitats, allowing fish and other animals to move into areas that were previously dry or shallow. Spinosaurus could use these conditions to access new feeding grounds. When floodwaters retreated, many animals became trapped in smaller pools or channels, increasing their vulnerability. These seasonal shifts created alternating periods of widespread and concentrated feeding opportunities. The presence of Spinosaurus also influenced the behavior of land animals that depended on rivers for drinking water. Herbivorous dinosaurs and other terrestrial species needed to approach water sources regularly, but the risk of encountering a large predator affected how and when they accessed these areas. Many of these animals likely adjusted their drinking times, moved in groups, or selected specific crossing points where visibility was better. This behavior reduced direct encounters, but also shaped how these animals used the landscape around rivers. The interaction between Spinosaurus and other large predators in the same region added another layer of ecological structure. While Spinosaurus focused heavily on aquatic prey, other predators may have relied more on land-based hunting or different aquatic zones. This distribution of feeding strategies reduced direct competition in some cases, but also created overlap in shared environments such as riverbanks and shallow waters. Encounters between large predators in these spaces would have influenced movement patterns and feeding timing. The juvenile stages of Spinosaurus played a different role within the ecosystem compared to adults. Younger individuals were smaller and likely limited to hunting smaller prey in shallow waters. This stage of life reduced direct pressure on larger aquatic animals and allowed juveniles to develop skills needed for later life stages. As they grew, their ability to capture larger prey increased, gradually shifting their ecological role within the same environment. The growth process also influenced how energy needs changed over time. Juveniles required frequent feeding on smaller prey, which meant they likely remained in areas with high concentrations of small fish and other easily captured animals. Adults with higher energy demands could target larger prey and cover wider areas of river systems. This change in feeding behavior across life stages helped distribute predation pressure across different parts of the ecosystem. The sensory abilities of Spinosaurus contributed to its success as a predator in aquatic environments. Detection of movement in water was essential for locating prey that might otherwise be hidden by turbidity or vegetation. Subtle vibrations and movement patterns in water likely provided important signals that guided feeding behavior. These sensory inputs would have been processed quickly to allow rapid response during hunting events. The interaction between Spinosaurus and sediment-rich waters also played a role in its feeding strategy. Many river systems in its environment carried large amounts of sediment, which reduced visibility underwater. In such conditions, reliance on sight alone would have been limited. Instead, movement detection and close-range strikes would have been more effective. The structure of its snout and jaw allowed quick snapping motions that could capture prey, even in low visibility conditions. The ecological pressure created by Spinosaurus feeding activity extended to reproductive behavior of prey species. Fish and aquatic reptiles often rely on spawning or nesting cycles that are timed with environmental conditions. The presence of a large predator could influence where these activities occurred, pushing them into areas with lower predation risk. This shift in reproductive behavior affected population distribution across the ecosystem. Large theropod dinosaurs lived during different parts of the Mesozoic era and were among the most prominent land-based predators in their environments. These animals include species such as Spinosaurus aegyptiacus, Tyrannosaurus rex, Giganotosaurus carolini, and Carcharodontosaurus saharicus. Each of these dinosaurs is known from fossil evidence that has been studied across many years by paleontologists working in different regions of the world. Their fossils come from rock layers that formed in different ancient environments, including river systems, floodplains, and coastal areas. The bones of these animals provide information about their body size, skull shape, teeth structure, limb arrangement, and general skeletal strength. These features help scientists understand how each dinosaur lived, what kind of prey it may have consumed, and how its body functioned in its environment. The fossil remains of Spinosaurus aegyptiacus have been discovered mainly in North Africa, especially in regions that today include Morocco and Egypt. The bones include parts of the skull, spine, limbs, and tail. Some specimens show long, narrow jaws filled with cone-shaped teeth. These teeth are not serrated and are shaped in a way that allows gripping, slippery food. The skull contains openings for nostrils that are placed farther back on the head, allowing the front part of the snout to stay in contact with water while breathing air. The vertebrae along the back are tall, forming a structure that supports extended neural spines. These spines are associated with a long sail-like structure along the back. The tailbones show adaptations that suggest movement in water, with long, flexible segments that support lateral motion. The remains of Tyrannosaurus rex come from North America, especially from rock formations in regions that are now the United States and Canada. The skull of this dinosaur is large and deep with strong bone structure and thick reinforcement around the jaw joints. The teeth are large, pointed and serrated, designed for tearing through bone and flesh. The arms are small but strong in muscle attachment, and the legs are long and powerful, supporting a heavy body. The neck is muscular and supports a large head. The tail is stiff and helps balance the body during movement. The overall skeleton shows a design suited for powerful biting action and strong movement on land. Fossils of Giganotosaurus carolini have been found in South America, especially in Argentina. The skull of this dinosaur is elongated and narrow in some regions, with rows of sharp teeth along the jaws. The teeth are blade-like and serrated, arranged in a way that supports slicing through flesh. The vertebrae in the neck and back are large and support a long body structure. The legs are built for movement across land surfaces, and the tail extends long behind the body, helping with balance. The bones show features that support a large predatory animal with a long skull and extended body frame. The fossils of Carcharodontosaurus saharicus are found in North Africa, especially in regions that include desert areas that were once river environments. The skull is large and filled with serrated teeth, similar in shape to those found in other Carcharodontosaurid dinosaurs. The jaw structure is elongated and contains many teeth arranged in a repeated pattern along the upper and lower jaws. The vertebral column supports a long body, and the limb bones indicate strong walking ability on land. The overall structure of the skeleton shows a large predatory dinosaur adapted to active movement in its environment. Other large theropod dinosaurs include species such as Acrocanthosaurus attocensis, which is known from fossil remains discovered in North America. The neural spines along its back are tall and create a ridge-like structure along the spine. The skull is large and contains serrated teeth used for feeding on large animals. The limb bones are thick and support a strong walking posture. The tail is long and helps stabilize movement. Another important sauropod is Mapusaurus rozier, known from fossils discovered in Argentina. The bones of this dinosaur include parts of the skull, vertebrae, and limb elements. The skull contains many serrated teeth arranged along both jaws. The vertebrae show strong attachment points for muscles, and the limb bones indicate a strong body structure that supported movement across land. The skeletal structure of these large theropods shows that they share a general body plan common to theropod dinosaurs, including a bipedal stance, a long tail, and strong hind limbs. The skulls of these dinosaurs vary in shape and size, with some having long, narrow snouts and others having deep and wide skulls. The teeth also differ in shape, with some being smooth and conical and others being serrated and blade-like. These differences reflect variations in feeding habits and feeding methods. The fossil record of Spinosaurus aegyptiacus shows adaptations linked to environments that included large bodies of water. The bones of the snout are elongated and the nostrils are placed in a way that supports breathing, while the front of the head remains near water surfaces. The teeth are shaped for gripping rather than slicing. The bones of the tail suggest movement that supports swimming motion. The limbs show a structure that allows movement on land, although the proportions of the limbs differ from those of many other theropods. The fossil evidence of Tyrannosaurus rex includes skull bones that are thick and heavily reinforced. The jaw muscles attach to strong ridges on the skull. The teeth are arranged in deep sockets, and replacement teeth form throughout life. The bone structure of the legs supports weight-bearing movement on land. The tail is made of strong vertebrae that help balance the front-heavy skull. The arms are small and contain two-fingered hands. The skeletal remains of Giganotosaurus carolini show a skull that is proportionally long and filled with many serrated teeth. The neck vertebrae are strong and support head movement during feeding. The body structure is elongated, and the tail provides balance during movement. The leg bones are large and support walking on land surfaces. The overall structure suggests a large predatory animal adapted to active movement. The fossil structure of Carcharodontosaurus saharicus shows a skull that contains many blade-like teeth. The teeth are arranged in a repeated sequence along the jaw, allowing continuous replacement during the animal's life. The vertebrae are strong and support a large body mass. The limb bones indicate a strong walking ability. The tail is long and supports balance. The fossil remains of Acrocanthosaurus atokensis include tall neural spines along the vertebrae. These spines form a ridge along the back. The skull contains serrated teeth that are curved slightly backward. The limb bones are thick and support movement on land. The tail is long and extends behind the body, supporting stability. The fossils of Mapusaurus rosei show skeletal elements that include vertebrae, limb bones, and skull fragments. The teeth are serrated and arranged along the jaw in a repeated pattern. The vertebrae show strong muscle attachment areas. The limb bones indicate a strong structure for walking and movement. The skull structures of large theropod dinosaurs vary in form. In some species, the skull is long and narrow, while in others, it is deep and robust. The arrangement of teeth in the skull also varies, with some species having cone-shaped teeth and others having blade-like serrated teeth. The placement of jaw muscles is reflected in bone ridges and openings in the skull. These features show how each animal processed food in different ways. The limb structure of these dinosaurs includes strong hind limbs with 3 main weight-bearing toes. The bones of the legs are thick and hollow in some areas, reducing weight while maintaining strength. The arms vary in size and function. In some species, the arms are small with limited range of movement, while in others they are larger and more functional in grasping motion. The tail is present in all these theropods and consists of many vertebrae that extend behind the body. The vertebral columns of these dinosaurs include cervical, dorsal, sacral, and caudal regions. The cervical vertebrae support the neck and head, the dorsal vertebrae support the torso, the sacral vertebrae connect to the pelvis, and the caudal vertebrae form the tail. The structure of these vertebrae includes muscle attachment points and neural spines. In some species, the neural spines are elongated and form visible ridges along the back. The bone microstructure of these theropods shows growth patterns that indicate changes over time. Growth rings in bones provide information about age and development. The internal structure of bones includes vascular channels that supply nutrients during growth. The density of bone varies depending on the location in the skeleton and the function of the bone. The skull openings in theropod dinosaurs include fenestrae that reduce skull weight and provide space for muscle attachment. These openings vary in size and shape depending on the species. The arrangement of these openings affects how the skull handles stress during feeding. The jaw joint structure also varies, affecting how the mouth opens and closes. The teeth of these dinosaurs are replaced continuously throughout their lives. Tooth replacement occurs in a pattern where new teeth grow beneath existing ones and move into position over time. The shape of the teeth reflects feeding behavior. Serrated teeth are suited for cutting through flesh, while smooth conical teeth are suited for gripping and holding. The fossil environments where these dinosaurs are found include river systems, floodplains, and coastal regions. Sediments in these areas preserve bones over long periods of time. Fossilization occurs when bones are buried under layers of sediment and minerals slowly replace organic material. The condition of fossils depends on burial conditions and geological processes over millions of years. The distribution of fossils shows that large theropod dinosaurs existed in different continents during different geological periods. The arrangement of continents during the Mesozoic era allowed movement of species across connected land areas. Fossil discoveries in North America, South America, Africa, and Asia show a wide spread of these animals. The limb proportions of these theropods indicate adaptations for movement and stability. The femur and tibia are strong bones that support body weight. The pelvis is connected to the spine and supports locomotion. The feet contain claws and toe bones that provide traction on different surfaces. The respiratory systems of theropod dinosaurs are inferred from bone structure and comparison with modern reptiles and birds. Air sacs may have been present in some species based on hollow bones and internal cavities. These structures would have assisted in breathing and reduced overall body weight. The nervous systems of these dinosaurs are inferred from skull cavities that contain brain structures. Endocasts of skulls show the shape of the brain cavity. Sensory organs include vision, smell, and balance systems, as indicated by skull bone structure. The feeding behavior of these dinosaurs is reflected in jaw mechanics and tooth wear patterns. Fossil evidence shows marks on bones that indicate feeding activity. Bite marks found on fossil bones provide information about feeding interactions in ancient environments. The study of large theropod dinosaurs continues through fossil discoveries and analysis of skeletal remains. New fossils provide additional details about bone structure, growth patterns, and anatomical variation across species. The skeletal features of these dinosaurs continue to be examined in laboratories and museums around the world.